Hello, I welcome you all. The problem reads if the motor draws the cable with an acceleration of 3 meters per second, determine the reactions at the supports A and B. The beam has a uniform mass of 30 kg per meter and the crate has a mass of 200 kg. Neglect the mass of the motor and the pulley. This problem is coming from the Engineering Mechanics and Dynamics, 14th edition by R.C. Hibbeler. Let's take note of this mass. This is for the beam, which we are going to use later on as we compute the supports. This is the mass of the crate that we're going to use when we compute the motion. Right, so we have the acceleration throughout this whole cable. Okay, so the acceleration is the same throughout, like so. Therefore, it means we have 2 AC equal to our acceleration, which is 3. Therefore, AC is equal to 1.5 meters per second. Okay. We can also write this in another way by drawing the positions. Let's say this is our reference. We have SC there, and then let's pick this point also. Let's say we pick this point is our, let's call it as our SM. Okay, SM, and then this one we call it SC. Okay, so let's now write down, relate this to the length. So we'll have SC plus SC minus SM equal to L, and this gives us 2 SC minus SM equal to L. Then we have 2 BC minus VM equal to 0. Taking this with derivative with respect to time, then we have 2 AC minus AM equal to 0. Therefore, given that our AM is equal to 3, therefore AC is just going to be equal to AM divided by 2, which is equal to 1.5. Okay, so that is the acceleration of the crate, and this is just a single crate. We are not going to use these equations to solve simultaneously like we are doing the other cases where we are assuming one direction. So we can take the motion, the direct motion of this crate. This crate is going up. Okay, so this crate is moving up. All right, not so. So we have our MA like so. Okay, then we do have our weight, which is just equal to mg, and this is equal to 200 times 9.81. This gives us, that's 200 by 9.81. This is 1962. Okay, newtons. All right. So let's do a section of this. We know that the tension force here is just going to be the same. Okay, tension force, we're assuming there is no friction between the pulley and the cable, so the tension force there is the same. It's the same cable going around, right? Okay. So we have the same tension, which is just T. Okay, right? Of course. So this is T, this is T. Okay, so let's write down the equation of motion. So we have 2T up, going up, okay, minus W is equal to MA. W, we already found this one, 2t minus 1962 is just going to be equal to 200. This is AC, so we are just plugging this there. Okay, do that, we just write 1.5 there. Therefore, our T is just going to be equal to, that's 200 by 1.5 plus 1962 divided by 2. So we have 1131 newtons, right? So 1962 plus 200 by 1.5 divided by 2. Okay. What else? This is about it. So let me do the section of this part and rewrite this. And if we did a section, then we'll have something like this. Let's not forget the mass. We do have the uniform mass there given, which I need to indicate. So let's write down the mass. We do have the mass there, so let me indicate it there like so. It is 30 meters. So we have this mass like so. I'm just indicating it there like so. We need to indicate this mass, I mean this weight. I'll need to multiply that mass by the acceleration due to gravity, so we convert it to weight. Okay, so this one, let's call it Q, and this Q is equal to 30 times 9.81, and this newtons per meter. So if we are to calculate this and get the equivalent acting at the center of gravity for the beam, which will be the midspan, because this one has its geometry is symmetrical. There we go. So this equivalent force just becomes Q by L, which is just equal to 30 by 9.81 by 6, and this is just equal to 30 by 9.81 by 6. This is equal to 1765.8. Okay, 30 by 9.81 by 6, 1765.8. Then we also found our T. So we do have T here. This is our T and another T there. Okay, and then we do have the reaction forces there on the simply supported beam. We have that one, we have this one, and then we have this one. All right, so what is this? So we have AY, we have AX, we have BY. This is T, this is T. Okay, do we have everything? And then we know that our T is just equal to 1131 newtons. So let's start with applying the summation of moments about point A and clockwise being our reference, and then I draw my reference somewhere there like so that I don't affect what I've already done. Alright, something like that. Then this just becomes we have T minus by 2.5, then another T by 3, then minus 1765.8 by 3, and then a plus by by 6 equal to 0. Here we are using static equilibrium equations, and we are supposed to do so. Okay, so let's replace these values there, and we'll also replace it there. Therefore, our by here just becomes equal to Let's find our by here. This just becomes equal to 1131. So 1131 by 2.5 minus 1131 by 3 minus 1765.8 by 3. Okay, then divided by 6. So we have a 19.65. Okay, let me check it. 1131 by 2.5, 1131 by 3, 1765 by 8 by 3 divided by 6, 19.65. Right, so there we go. So let's find the other one. So we have summation of forces in the y equal to 0, going up being our reference. So we'll have by plus ay minus 2t minus 1765.8 equal to 0. Therefore, our ay is just going to be equal to 1919.65, okay, minus 2 by 1131 minus 1765.8. So we have 2108.15 newtons. Let me check it again. 1919.65 minus 2 by 1131 minus 1765.8, 2108.15. Then finally we have summation of forces in the x direction. What do we have? Of course, ax there is just equal to 0. Okay, there we go. So we have by, by like so. We have ay, we have ax. Okay, we have ax like so. Okay, I think this is really about it. We have found the values of ay, by, and ax for the beam. And I hope this particular problem was helpful. This video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.